Nathan, we're going live, so we need audio silence. Just an FYI. Check one.
Okay, you just put this in the back.
Sure. All right, thank you. Hi there, how are you? Nice to see you again. Yep, sorry I didn't give you guys too much time to look through it. So I'm in a rush.
Okay, good afternoon, everyone. It's my pleasure to introduce today's Science of SLAC lecture series speaker, Dr. Hao Yan. Hao is a joint postdoctoral fellow at Stanford and SLAC and a member of the Stanford Institute of Materials and Energy Sciences, SIMES. He received his PhD from Harvard University in 2011 and is an author of 20 peer-reviewed papers and patents. In his lecture today, Dr. Yan will describe the discovery, fundamental studies, and applications of an exciting new form of molecular scale diamond particles called diamondoids. His lecture is titled Molecular Bling, The Surprising Properties of Small Diamonds. Please join me in welcoming Hao.
Thank you, David. It's a pleasure to be here to share with you some of our recent discoveries on this really amazing molecular scale diamond and how we put into use for some either both fundamental science and some device applications. So before I start, I just want to give credit to the people who lead this work and who actually did the work. So we are an international team led by several professors both here and abroad. We have Professor Nick Melosh, Shen, both faculty at Stanford and SLAC. Jeremy is a geophysicist that was originally associated with Chevron, and he joined us in, I think, 2008. And he was one of the first discoverers of some of these really amazing molecular scale diamonds. And then we have Professor Peter Schreiner from Germany. He's an organic chemist, and he did a lot of these chemical modifications of this diamond species for us. Here are some of the students working on this project, and we have several collaborators, both from academic and from industry. So here's the outline of my talk. I'm going to show you what are these diamondoids, or as we define it, the molecular scale diamond, what are their structures, how we discover them, and what are some of their properties. Then I'm going to show you two examples how we use this unique type of material, of diamond material, and put them to some really new applications. Basically, how we use them to direct the synthesis of novel semiconductors, and how we use them to enable single color electron sources that are useful for both imaging, for lithography, and a lot of other applications. Then I'm going to give you a few thoughts on what we think the future would be regarding this material. So when we think of diamond, well, most of you would think, as I do, would think about it as a fine jewelry. It turns out it's more than that. So if you look at this chart, this is the annual diamond assumption. The use of diamond as gemstone only takes about 5% of the whole use. You have this big chart here, which I didn't mark, but this is a synthesized diamond. You have also this part, which is the mined diamond that are used for industrial purposes. And this is really because diamond has a lot of amazing properties. We all know that it's a very hard material, it's a good thermal conductor, but there are also a lot of other things. For example, this super hardness and also the surface property of diamond made them a very ideal materials for example, precision machining and for microelectromechanical systems. The diamond has very unique electronic properties, as I will tell you later in this talk, making them very good electron sources, and they are biocompatible, and they can bind drugs, so you can deliver drugs using them into, say, specific cells and tissues. And most recently, people found that certain defects, or what we call the envy center in diamond, can hold a spin, that is the self-rotation of electrons in it, and that can be used to carry out some of the advanced quantum computings. So here I want to talk a bit about how size affects the properties and applications of materials. We have been all been hearing about this nano for about a decade, or almost 2 decades now. And what people have found in this long research is that when you change the size of materials, you also change the properties of them. It's not just that they're shrinking, but they enable, or new properties emerge as the size shrinks. So one of the examples, probably most well-known example, is this size-dependent color of gold colloids. That's very tiny gold nanoparticles. You can see here, as you change the size of these particles, that is the diameter of the particles, from 2 nanometer up to 150 nanometer, you have a whole range of different colors ranging from them. That really comes from the size-dependent electronic properties of these tiny gold particles. And this actually was known for centuries long, and this was actually what people used to tint the windows in churches, as we see. So coming to diamond, or coming to carbon materials, what happens if you shrink the size of them? Well, besides diamond, the other family of carbon material that's very well known is graphite. And when you shrink the size of graphite, you have all kinds of interesting materials. You have this closed shell fullerene, when you have a single layer of carbon, you can either lay them out and have a graphene, or you can roll them up to have carbon nanotubes. And these have really very, very different properties from their bulk counterpart, as the graphite, for example. Carbon nanotube is known as one of the lightest yet strongest material. It's stronger than steel, yet much lighter than steel. And for graphene, which was discovered just the past decade, it was found that how the electrons move in this two-dimensional plane is quite different from how they move in a three-dimensional space, and this gives rise to a lot of interesting applications, for example, for ultra-fast transistors, for light detecting devices, etc. So what about diamond, the other type of carbon? What happens if we shrink their size? Do they give us new properties, and what do we expect from them? Well, let me first talk about why we care about shrinking the size of diamond, or why we care about shrinking the size of materials in general. There are two major effects that we are interested in. For one is the surface effect. That is, if you have a bulk material and you cut them up, the smaller particles you cut them into, the more surface you expose. And with more surface means that you can, for example, carry more drugs per each particle, or you can expose more active sites to catalyze certain chemical reactions. And the other aspect is what we call the quantum confinement. That is, the electronic properties of certain materials changes as you shrink the size. And I show here, this is what we call the band gap. You don't have to know what exactly it means, but it's basically the color of light that a material can absorb. And you can see that as you change the size of certain materials, this band gap, or the color it absorbs, start to change. And it also happens in diamondoid or in nanodiamond. So this really allows us, if we can find ultra-small diamond, to make new electronic materials and new electronic devices. Okay, before I talk about actually making or trying to find nanodiamond, I would like to guide you through what I call a thought experiment. So first, let us look at the structure, the atomic structure of diamond. So diamond is nothing more than a three-dimensional array or lattice of carbon atoms bound in such a way that each carbon is bonded to 4 of the neighboring carbons. So this is the three-dimensional view of the lattice. And if we take that and we project it onto a two-dimensional plane, this is what we have. Now you can start to see that there are edge atoms, and there are, let's say, bulk atoms or central atoms. Now what I want to do is, I want to take these edge atoms one layer at a time, and as I do that, I'm shrinking the size of this, let's say, chunk of diamond. And as you do that, you can imagine some of these carbons that were originally in the bulk or in the center are now exposed to the edge. And what happens when you do that is that you expose some of these carbons to the edge such that the 4 bonding, that is, each carbon is bonded to 4 neighboring carbons, cannot be satisfied for these carbons. So what we do is we take a hydrogen atom and we use that to saturate the unsettled or dangling bonds that are on these edge atoms. And we keep shrinking the size, keep shrinking, until we come to the point where if you shrink more, you don't have this intact diamond lattice anymore. So this is a two-dimensional view, and we roll it up. Now what you have is the smallest conceivable diamond lattice or diamond structure that you can have. This is actually what we call adamantane. It contains only 10 carbons, and you have hydrogens on the outer rim where the carbons cannot bind to other carbons. So this is a sort of a thought experiment to show you how we conceive a small or ultra-small nanoscale or even molecular scale diamond. Do they exist? Well, the answer is yes. One way people make that is quite surprisingly using a very violent method. What they do is you take some highly explosive chemicals like TNT, you put them into a stainless steel jar, or what they call a bomb, you seal it, and you just set it off. Well, as you can imagine, what happens is that there's a very violent explosion in there. And what comes together with that explosion is very high temperature and very high pressure. And when that happens, just like when diamonds was made in the center of the Earth, some of the carbon species in these detonates turns into diamond. And here is a picture of what you got from this. Literally, people had to scratch these grayish suits off the wall of this bomb in order to get this. So you can see these are really not like what you would expect for a normal diamond. These are grayish, almost suit-like materials. And what's actually in there is when you put it under a microscope, you can see that they are composed of tiny particles of various sizes and shapes. And if you zoom in further, this is using transmission electron microscopy, you can see an array of these tiny dots. Each of these dots represents a column of carbon atoms, and by looking at the spacing of these dots, you know that, well, this matches the lattice of diamond, so we know that this is diamond. But this is really poor diamond, I would say. What people found was that there are a lot of defects in there. That is to say, not every carbon is bound to four adjacent carbons. There are dangling bonds. There are positions where you're missing a carbon. And what's more serious is that because you're using highly explosive materials to produce them, they contain a lot of heteroatoms, that is impurity atoms such as sulfur, nitrogen, and phosphor. And not to say that they come in all different sizes, different shapes, different chemical compositions. So this is really not an ideal diamond that we would like to work with. So, sure. So basically, it's called TNT. It's a benzene ring with 3 nitro groups, 3 NO2 groups on it. Sometimes people will put in some catalyst, but it's not that critical. The main thing is the highly explosive chemical. So the question that we want to ask is, can we somehow achieve a diamond that's sufficiently small to be interesting, but that's also chemically pure, that's pure both in their composition and in their shapes and in their sizes? Well, the answer is that you cannot find them in a jewelry shop, but surprisingly, you can find them in an oil well. So this is the smallest diamondoid. As I just showed you, this is adamantane. It is 10 carbon, what you call it a small diamond or even a molecule. It's the smallest possible diamond structure that you can conceive. And this was actually found in oil well in Central Europe in the 1930s. And later, it could be synthesized by organic synthesis in the 1940s. And similarly, people were able to find a diamantane that is 2 of these adamantane cages merged together. You can think of it as a 2-cell diamond, also in the oil. But for the last, let's say, 60 to 70 years, that's about it. That's the whole, let's say, arsenal that people have in terms of chemically pure, shape pure, and size pure molecular scale or nanoscale diamond. Then the breakthrough come in 2003 when one of our scientists, Jeremy, who's sitting in the audience, he was working with Chevron at that time, and what they found was that they were looking at these oil wells, and frequently people found that some of these oil wells got clogged by a whitish crystalline material. So it's puzzled a lot of people what they actually are, but nobody really looked into it. And Jeremy and his colleague actually took some of these materials, distill it, and try to separate them using what we call chromatography. That is a powerful tool to separate different species from mixture. And what you end up finding is this really pure white crystalline structure, crystalline materials. So this looks really, really different from that grayish suit thing that I showed you, indicating that this is not some, highly impure mixture of different species. And they did some further analysis. Well, again, this is published in Science in 2003. And when they did some analysis, they found that there are amazingly a wide variety, a huge family of different diamond or diamondoid structures in there. Now, each of this structure is not, I just want to remind you, is not a cartoon, but is actually a chemical species that they can separate, and we can actually hold each of these in a small vial, use them as chemicals or use them as materials. They are available in a relatively large quantity for us to play around with them. So this is really a very exciting discovery in that we now have a much larger arsenal, a much larger, let's say, playground of diamond or diamond-like materials that we can play around with and to explore their unique properties. So again, to compare the two species, what we know as the nanodiamond, that is the diamond made by setting off TNT in a jar, and what we call as diamondoid, that are these chemically pure, shape-specific and size-specific diamond molecules or diamond structures that was extracted from oil, what we call this as a diamondoid. You can see that just from the appearance, they're quite different. One is a grayish or black suit containing a lot of different sizes, shapes, chemical composition, etc. The other one, you can have them available as a chemically pure and also size and shape pure chemical. And if you take a microscopic look at these two species, again, this is under TEM, this is under STM, what you see is that with the nanodiamond, that is the diamond by detonation, you have really a wax-like mixture of different species. With the diamondoid we found in the oil, you can see that each of these bright dots represents one single molecule of diamond sitting on the surface. They're really, really pure and they're really, really, really uniform. So this is something that nobody was able to have before, and now we have them in large quantities, in large varieties, and this really gives us a very exciting playground to explore some of their applications and the properties. Okay, so now I'm going to show you two examples how we take this unique, newly found diamond material and put them to some use. The first one I'm going to tell you is how we use the diamondoid to synthesize novel semiconductors, what we call a Lego game at molecular level. So let me remind you of the different diamondoids that we have in hand. And remember, because this is a diamond structure, it's essentially a cage-like structure. And what that means is that it's very rigid. You cannot twiggle it, you cannot tweak it around, you cannot shake it around. It has a very well-defined shape. And they also come in different shapes as well. For example, this tetramantane is more like a pyramid. We have a rod-shaped, this is a pentamantane, rod-shaped pentamantane, and you have this L-shaped tetramantane, etc. So what does this remind us? Well, actually it reminds us of Lego. Lego is also a size and shape specific, let's call it species. It comes in different sizes, different shapes. You can put them together to build some really fancy things. So what we think is, well, can we take this diamondoid and play a Lego game, but at a much, much more smaller scale? How small? Well, a diamondoid compared to a Lego is sort of on the same level as a Lego compared to our Earth. The other reason why we think this is really a feasible idea is that people have found really unique behaviors in this diamondoid species or diamondoid materials. What I show you here is two diamondoid, or a few species of two diamondoids bonded together by a carbon-carbon bond. Now remember, in normal hydrocarbon, in normal organic molecules or species, the length of the carbon bond is about 1.5 angstrom, and the length of the carbon bond is a measure of how strong the bond is. Now, normal length being 1.5 to 1.6 angstrom, what we found was that in these species where two diamondoids are bound together by a carbon-carbon bond, the bond length is astonishingly long, about 1.7 angstrom, 10% longer than any other carbon bond that people have known of. Now, under normal circumstances, such a long bond would mean that the bond would just simply not exist. It's too long that it's not stable and it's going to break apart. What's really surprising is that people found these molecules, these species, actually exist and quite stable. And the reason is that because these two diamondoid molecules have a very strong attractive force between them, so this force compensates for this ultra-weak carbon-carbon bond that link them together and sort of hold the bond together to make this species stable. And the revelation we have here is that this non-bonding interaction between the diamondoid molecules is so strong that it effectively influences the behavior of the bonding formation in these molecules. So a non-bonding interaction that affects the bonding behavior is something that nobody has ever seen before, and diamondoid is really the key material to enable this. Okay, so pardon me? So the attractive force is basically just dispersive van der Waals force. Well, since this is one way of utilizing this ultra-strong non-bonding interaction, can we invent other ways? Can we use this strong bonding to enable other materials? So this is one thing that we tried. What we do is we take a diamondoid and have our organic chemists modify it such that we connect a sulfur atom to one of its tails. Now this sulfur atom can then react with certain metal species like silver. Now when we mix them together, what we end up having is this wire-like species. People know that when you put these two things together, what happens is that the silver or the metal species bind with the sulfur, and they form a long chain of alternating metal-sulfur, sort of like a polymer, but instead of a polymer being formed by carbon-carbon bond, this is formed by a metal-sulfur bond. And then you have the diamondoid sitting around them like a side group or like a shell. Now what's unique here is that we tried a lot of different diamondoids as well as other hydrocarbon species with a sulfur atom at its end. What we see here is that as long as you use a diamondoid and mix that with a metal, you end up having these wire-shaped, highly crystalline materials. But when you use a hydrocarbon, a normal hydrocarbon, that is one species with a long carbon chain, which does not have this cage-like rigid structure, what you end up having is this wax-like structure. It doesn't have a really crystalline appearance. So what this says is that the existence of the diamondoid and the interaction between the diamondoid really modifies the behavior of the crystal growth and really enables the growth of these highly crystalline materials. And we can do it for a lot of different species. We can do copper, we can do silver, we can do cadmium, we can do mercury, we can do lead. And on the diamondoid side, we can bond them to all kinds of different diamondoids with different sizes, shapes, and they end up having different morphology in the crystal that they grow, but they all end up having a very highly crystalline material structure. So next question is, how do we know what's actually the arrangement of atoms and molecules in these crystals? To do that, we just take one of the crystals that we grow, we mount it onto a goniometer, and we bring it to the beamline at SSRL, and sometimes we do ALS as well, and we use a very powerful very powerful X-ray beam generated by the synchrotron radiation to generate a diffraction pattern of them, and using the diffraction pattern, we can solve the atomic structures. And here we have an amazing gallery of different species showing very different behaviors in how these atoms arrange themselves. What they have in common is that you have a long chain of alternating metal and sulfur atoms forming this backbone and elongating along the long axis of the crystal, and then you have the diamondoid species going surrounding them. But the exact way how they arrange themselves is quite different, and that's really modified by the diamondoid species. For example, shown here is a silver adamantane thiolate that is a silver sulfide with a diamantane surrounding it. You can see that you have two pairs of silver-sulfur chains bonding together, and then you have the diamondoid sitting in what we call a cis position surrounding them. And then when you look at the copper adamantane thiolate, what you have is instead a rosette structure where you have 6 diamondoids surrounding them and having a hexagonal sort of copper sulfide in the center. And then when you change that adamantane to diamantane, it totally modifies the structure, and then you have this very different crystal structure. So let us take a closer look at one of the examples. This is the copper adamantane thiolate that is a copper sulfide in the center with adamantane surrounding it. What we have here is really a molecular wire, as we call it. What you have is a cable-like structure with a copper sulfide that is 3 copper, 3 sulfur, and stacking together in the core, forming this long chain of copper sulfide. And then on the outer rim, you have the diamondoid surrounding this core, really forming a core shell cable kind of structure. And to remind you, this is really atomic perfect, and this is ultra thin in nanowire. This is only 3 atoms thick in the core, and I don't think anybody else was able to make a nanowire this thin. Now comes the question, what happens if we change the adamantane to diamantane? Well, by a naive thinking, which we originally had, was that, well, you have a core shell structure to start with the adamantane. Now, diamantane is nothing more than just adding one more cage to the adamantane. And what we initially thought was that, okay, you still have the same structure with the same copper arrangement of copper and sulfur species, but you only have a thicker shell because of a larger diamondoid. And what we found really surprised us. So with the diamantane, you totally break the symmetry of the arrangement of copper and sulfur atoms as you have in adamantane. Instead of having a triangular stacking of copper and sulfur atoms as in the adamantane, here what you have is a square linked together with a rectangular sharing one edge, forming, instead of a molecular wire kind of structure, this is more like a twisted ribbon kind of structure. And again, this is surrounded by the diamantane species around it. And what happens here is the only thing that has been changed here is that we're changing from adamantane to diamantane, and by varying the size of the diamondoid, we're changing the interaction between these diamondoid species. And as you can see here, this change is so large, so significant, the interaction is so strong that it starts to modify how this covalent or how this bonding formation between the copper and sulfur atoms in the core behaves. So this is something that I don't think anybody else has been able to observe before in the growth of this one-dimensional or in general in material synthesis. Now with the change of the arrangement of atoms comes naturally the change of electronic properties. And to probe that, what we do is we essentially looking at how they absorb light and how they emit light, what we call light absorption and light emission. And this is important. Well, basically light absorption is just what color the crystal appears, and this is really important for applications such as to harvest, let's say, the sunlight and convert them to energy. And what you have here is that beyond, let's say, 600 nanometer wavelengths, the crystal, both crystals, doesn't really absorb much light, but you start to see strong absorption with the adamantane around 500 nanometer, that is in the greenish regime, but with diamantane, because of the different arrangement of the copper and sulfur atoms, again, enabled by the different interaction between the diamondoid species, now you start to have an absorption edge around 400 nanometers. So this is really a huge 100 nanometer change in the absorption edge, indicates a large change in their electronic properties. And this is, again, solely enabled by changing the arrangement of copper and sulfur atoms in the species, again, enabled by tuning the interaction between the diamondoid species in a non-bonding environment. Similarly, when we look at how they emit light, which is again useful for example, LEDs and other illuminating devices, you see quite different emission peak from the adamantane copper sulfide and the diamantane copper sulfide. One is centering at about 800 nanometer, the other one around 600 nanometer. So again, huge difference changed, induced in these materials solely by changing the non-bonding interaction between the diamondoid species. Okay, so to briefly summarize and to look forward on this part, what we have is essentially a new type of nanometer scale semiconductors. And this is really analogous to semiconductor nanowires. These are basically semiconductors with one-dimensional semiconductors with a diameter in the range of a few tens of nanometers. And these semiconductor nanowires has been found to be really useful for a lot of applications, for example, to build computer chips, to build energy harvesting devices, and to control and store spins. That is how electrons rotate around themselves in them. And for a lot of these applications, what is essentially needed is really well-controlled small diameter, uniform diameter, and free of defects. And now this has still been challenging for the conventional semiconductors synthesized by atom masses. But what we have, we think, is quite hitting on the spot. We have a molecular size thickness of this wire. Remember, in this copper sulfide with adamantane, we have essentially only 3 atoms in the cross-section of the copper sulfide core. We have a very well-defined atomic structure, and we have the diamondoids surrounding them as a surface protection, so you don't have surface defects such as dangling bonds and add atoms. And by using different diamondoids and different, let's say, metal species, we can tune the electronic properties to suit them for different needs. And this is really, again, enabled by having the diamondoid as a non-bonding tuning factor to control the structures of the growth of these molecular wires. Oh, that's a very good question. So what we observe is that these crystals can grow really, really long, sometimes up to millimeter size, if you just give it enough time. All right, so now I'm going to shift gear a little bit and talk about another application that we found in this diamondoid, that is to use them to create single-color electron sources, well, what we call an analog to a laser, in the sense that laser is basically a single-color light emission, and here we're trying to create a single-color electron emission. So again, I want to start by revisiting the property of diamond. Diamond has a very strange property in that it doesn't really hold or doesn't really like electrons. Once you draw an electron to the surface of diamond, it just spontaneously, well, kick it off and let it fly into the vacuum. And for this reason, diamond has been made into a very efficient, what we call a field emitter or electron source. That is, you fabricate this pyramid or needle-shaped diamond, you apply a voltage on the back of it, and you have another electrode, let's say, far away from it to work as a counter-electrode. And we have bias between these two electrodes. Electrons are just drawn out of this diamond species, and they form electron beams. And why do we care about electron beams? Well, electron beam is basically like light beam, only that they're more powerful. What I show here is what we call a transmission electron microscopy, and what they do is that you take a beam of electrons, you focus it, and then you shine it on certain species. And with the electron beam shining on species, and by analyzing how the electrons change their behavior when they pass the species to be studied, you can do all kinds of imaging to very high resolution. For example, shown here are just a few examples. This is one of our collaborators' work. This is basically a carbon nanotube. What you're seeing is the sidewall of the carbon nanotube. And what's amazing here is that you can actually see individual molecules of diamondoids that are inserted into them purposefully. Another example would be this high-temperature superconductor, the YBCO, sitting on a substrate. And what you're seeing here is each of these bright dots is a column of single atoms. And you can have atomic resolution to see the interface and the different layers in the substrate and in the YBCO. And they can also be used for biological species. Shown here is the TEM image of virus, which happened to be Ebola virus. You can really see the shape of the virus. This cannot be reviewed by other techniques to these great details. So this is really a powerful tool. It has applications in a lot of different categories or disciplines in fundamental science and applications. But a critical limitation that sort of narrows the application of this technique is the brightness. And the reason is that when we take a diamond or take a field emission material and generate electrons out of it, what you have is really sort of a messy or dirty bunch of electrons. They have all kinds of different angles when they go out of the surface. They have different kinds of energies as well. And to do really high resolution imaging, what people do is they sort of slice this really broad range of electrons and just take a very thin piece of it. The ratio between the electrons that are actually useful and the electrons that you actually draw out of this material is about 1% or even less. So even if you generate a lot of electrons from this electron emitter, say of diamond, only a very tiny part of them can be useful. And because of the need to filter out a lot of the unuseful or, let's say, harmful electrons, it requires really a lot of instrumentation to do that. Shown here is a state-of-the-art TEM machine that was housed in Ohio State. You can see that it's really like the ENIAC of computers made in the 1950s of the last century. It's basically a huge, gigantic machine that takes up the whole room to work on. And this is really inefficient. We know that, well, diamond has these unique properties of generating electrons, and now we have these diamondoids. So the natural question that we want to ask is, well, can we take these diamondoids, and because they are just a molecular level thin, you can transfer them onto other surfaces, and we want to know whether this diamondoid modified surface would give you a cleaner electron emission, or on a more fundamental level, what's the electron emission behaviors like when you have a diamondoid species on another surface. So this is what we do. We take, again, a diamondoid, in this case a tetramentate, a 4-caged diamondoid. We modify it with a sulfur atom on the end such that it can be bound to a gold surface. It forms a self-assembly monolayer, that is a monolayer of this diamondoid species standing up on a gold surface. And we shine light on it, and what we care is how the electron number depends on the kinetic energy. So instead of this really broad distribution of the energies coming out of the surface with the diamond, with the diamondoid, what we have is a really sharp, almost monotonous, monochromatic, that is single color peak as a function of the kinetic energy. This single peak takes up about 60% of the total electrons coming out of it. So what happens here, as we think, is that because we're having a very thin layer of diamond, and because they're so chemically pure and so structurally pure, such that the electrons doesn't behave differently when they come out as they do with a diamond surface, which has all kinds of defects and all kinds of atomic arrangements and all kinds of local chemical environments, which can all influence how the electrons come out of them. In this case, with a diamondoid, because it's so pure a material and it's only a monolayer, molecular monolayer thin on a surface, when the electrons come out, they decide to, well, all come out with the same energy. And this is really exciting. And just to compare that with a bare gold surface where you don't have the diamondoid, again, you have this very broad peak spanning about 20 eV, whereas if you have the diamondoid on the surface, the peak width is only about 0.2 eV. So we're really creating sort of a energetic funnel where we take a very broad range of electron energies and just squeeze them into a really sharp peak. So instead of throwing away all these electrons that doesn't have the right energy, now we can concentrate them into the single peak and make them all useful. And this sort of is analogous to what's been developed here, the LCLS, which is a free electron laser, in the sense that the LCLS was trying to create a monocolor, highly bright X-ray beam, while what we do is to create a monocolor, highly bright electron beam. Now, I believe these are different techniques, and they can look at different properties or different aspects of materials. But just to remind you, the LCLS is sort of a kilometer long construction, while what we have is the diamondoid photometer is a molecular layer on a piece of wafer. So with this new technique, we're very excited, and we want to find some real application for it. So we talked to some of the instrument manufacturers out there. For example, we're in active collaboration with KLA Tencor, and we're trying to put one of these diamondoid-enabled single-color electron emitter into their, for example, lithography tools or electron microscopies, and see if they can actually work. as an electron source. And here they just gave us some of the requirements for their emission source. Basically, it has to have a narrow enough electron energy distribution. It has to have high enough brightness. And these criteria we can all meet with the diamondoid species. The only thing that has been stopping us to put it to real use is the lifetime. You can imagine that because this is only a single molecule, a monolayer of molecule bound on the surface by a single atom, this is really, really unstable, especially when you operate it by bombarding it with a lot of phonons and having a lot of electrons coming out of it. So eventually they just fly off the surface, and when they fly off the surface, this sharp peak disappears. So what we can do then is that we take the diamondoid and we bring in another, well, its cousin, another type of carbon material that is graphene, and we lay them together. And what happens here is that graphene is a very dense monolayer of carbon. It's mechanically robust such that it sort of confines these diamondoid species on the surface, not letting them fly away from the surface into the vacuum. But because it's very thin, it's only a monolayer of carbon, it's really, really transparent to electrons. So whatever electrons you extract from the diamondoid, you can still send them into vacuum without being bounced back or bounced sideways by this graphene coating. So again, we look at the number of electrons as a function of their energy. You can see that we preserve this really sharp, what we call single color or monochromatic electron emission peak, and this can now be operated really over a long range of time, a long duration of time. And it's not only stable to radiation, it's also stable to temperature. And this is also important because for actual use of this electron sources, you need to bake them from time to time to get rid of the contaminants. And when you do that, you need to heat up the electron source to about 200 degrees. And this is simply not possible if you only have a monolayer of diamondoid on this gold surface. They would just be boiled away into vacuum. But with the diamondoid, with the graphene coating, we're again confining this diamondoid species on the surface, and it prevents the dissociation of the diamondoid species from the surface. What we show here is the XPS spectra of the sulfur. Basically, it's a signature of whether the diamondoid exists on the surface. You can see that with the bare diamondoid, at room temperature, you can have a very sharp peak indicating that they are actually on the surface, but when you heat it up to 200 degrees, the peak is gone. When you have the graphene protected diamondoid, initially you also have the peak, and that peak is preserved when you heat it up to 200 degrees, showing that the species is confined to the surface by this graphene coating. So we think that we're on the right track to create a really stable and monochromatic single color electron source. And what can we do once we have that in hand? Well, we can do a lot of amazing things. For example, because the electron beam is so bright now, because you don't throw away all these other unusable electrons, now you can do really, really short time exposure on species such that you can monitor the motion, for example, of biospecies like an enzyme in working, for example, to look at how enzyme opens up certain, let's say, active sites, take a target material and produce the desired molecules. You can also use that to monitor chemical reactions in real time, for example, to see how precursor species diffused onto a catalyst, how that's converted to other species, how that's released. And because it's a very bright beam, you can use that to do ortholithography, that is to create nanostructures on a surface, and this can allow us to make more powerful computer chips. And beyond all of this, because this is a technique that's enabled by merely coating a monolayer of molecular species on a surface, it really helps to miniaturize instruments, takes what is now taking out the whole room to operate into something that you can operate, let's say, on a benchtop or even handheld. That's probably too far. So, to summarize, I hope that I convince you we have in hand a really, really unique material that is a diamond, but that has access to the dimension of diamond that nobody else was able to attain before. And with these materials in hand, we can study unique diamond-like properties, and we can enable new material synthesis and new devices. So with that, I end my talk. Thank you for your attention, and I welcome your comments and questions.
Questions?
So I'm fascinated that the source of the diamondoids is the most promising source is digging them out of oil.
Mm-hmm.
Is there still work being done on the production techniques for producing the diamondoids using the detonation techniques, for example, or where are most of your diamondoids coming from?
So most of diamondoids are coming from still digging in oil well.
Okay.
We are developing some techniques where it allows you to take a smaller diamondoid, like adamantane, which is more abundant, and use as a template to synthesize larger diamondoids. This is a technique under development.
Okay.
I guess I had a question just following up to that one. How do you separate the different sort of flavors of diamondoids?
I guess this is more of a question for Jeremy, but I'll try to answer it to the best of my capability. So what happens is that these different diamondoids, they're very similar in their chemical properties, but they're very different in their size and shapes. So what you can do is you can design a path, or what we call a column in this chromatography, in this separation tool, that only allows certain molecules of certain sizes or certain shapes to pass through while retaining other sizes and shapes. So by designing this pathway or designing this column, you can selectively separate a certain species of diamondoid while retaining the others in the pathway without letting them go through. And this can be confirmed later by using other techniques like mass spectrometer to see that we're actually getting what we think we're getting.
Yeah, I have another question. This is an application question.
Mm-hmm.
You did bring up, I guess, one example of sort of a photonics type application, which was LEDs.
Mm-hmm.
I'm wondering if you guys are also looking at other photonic device manufacturing using the diamondoids as kind of the building block again, sort of the Lego to build up different types of photonic devices.
Well, for one thing, the diamondoid themselves, with the proper size and shape, can be a light emitting device, but that really emits in the very deep UV regime. The light emitting device that I was talking about is really when you use diamondoid as sort of a template or a guiding material to allow the synthesis of other semiconductors, in this case copper sulfide. We're also looking at cat sulfide and other species. And by changing the diamondoid size, change how the atoms bind in these metal sulfides or metal selenides, and in turn using that to change the emitting wavelengths or emitting color of these species. So I'd say yes, we're looking at different species.
So sort of using it sort of as a scaffolding for other materials that you're producing, the semiconductor materials. Okay.
Yes.
Question here.
I have a question. How stable are those nanorods which are composed of these diamondoids and those, along with that silver and sulfur bonds?
Oh, these are actually very, very stable. I mean, we didn't really see any possible degradation of it. I mean, if you heat it up to some temperature, we haven't really done that, but I'm sure above certain temperature, this carbon-sulfur bond is going to break, and you will end up having some metal sulfides, and the diamondoids are just going to be boiled away. But in terms of, let's say, degradation in air or degradation under, let's say, light illumination or radiation, we really don't see much of that. It's quite stable. And the other thing that I just want to bring up along this line is that this diamondoid coating actually really stabilizes some of the normally unstable chemical valences. For example, one of the copper sulfide structure that I showed you there, the copper is in the copper 1 state, which is normally unstable in air. It turns into copper 2 very quickly. When you have the diamondoid surrounding them, it stays in copper 1 for a very, very long time. We don't see any degradation of it. So in a sense, the diamondoid, sort of like a shell, is a protecting agency that stabilizes actually the semiconductor core in there.
Does it mean that you have not gone beyond 200 Celsius just to check the degradation?
Just to check the degradation? No, we haven't. We haven't really tried to pyrolyze this thing. What we're interested is what are the properties of them in the S-grown form, I'd say.
Okay, thank you.
Yeah. I guess, again, the really unique property here is that you don't have to throw away the electrons that are not in the right energy regime. That's the major uniqueness here. We're also trying to make some field emission devices using the diamondoid, but there, I guess the physical mechanism is quite different. Instead of having the electrons absorbing photons and then coming out, now you're relying more on the tunneling process, and we are still looking into how the different physical mechanisms affects the distribution of electron energy when they come out of the diamondoids. But I'd say the major advantage of having a diamondoid is that it generates a very, very narrow electron, a beam of electron in terms of energy.
Okay, if there's no further questions, let's thank Hao one more time.
Thank you.